The big discovered is bigger than your imagination. You think you understand what the word big means. You've used it your entire life. Big cities, big mountains, big storms. Even in space, you've been told about big things. Planets so large they could swallow Earth's whole. Stars so massive they burn millions of times. Brighter than our sun. You've probably heard that our galaxy contains hundreds of billions of stars and stretches. Across distances so vast that light itself needs 100,000 years to cross it. All of that feels enormous, intimidating even. And yet, none of it prepares you for what you're about to encounter. Because the galaxy we're talking about isn't just big in the way those things are big. It doesn't simply scale up what you already know. It breaks the scale entirely. It reaches a size where comparisons stop working, where numbers lose their meaning, and where your imagination begins to fail not because you aren't smart enough, but because the human mind was never built to operate at this level of reality. This isn't dramatic storytelling or poetic exaggeration. It's a statement about biological limits. Your brain evolved to judge distances measured in steps, sizes measured in arm lengths, and time measured in days and seasons. Even when you stretch that intuition to include continents or oceans, you're still operating within a framework that makes sense to your nervous system. But cosmic scale does not play by those rules. It doesn't care what feels reasonable or intuitive. And when you confront the largest galaxy ever discovered, you cross a threshold where size stops being something you can imagine and becomes something you can only accept intellectually. Like a mathematical truth you can't visualize. At first, your instinct will be to compare it to things you already know. That's what the mind always does. You'll try to anchor it to the Milky Way, to the distance between galaxies, to the age of stars, to the speed of light. You'll tell yourself, okay, it's bigger than our galaxy, maybe much bigger. But that approach collapses almost immediately. Every comparison you reach for will either undersell it or overwhelm you. The gap between what you expect and what is actually true grows so wide that your sense of proportion starts to dissolve. It's like trying to imagine a color your eyes were never designed to see. What makes this galaxy truly unsettling isn't just its size, but how casually it exists. There's no explosion announcing it, no dramatic boundary marking where it begins or ends. It simply sits there, over 1 billion light-years away, containing more stars than you could count if you dedicated millions of uninterrupted lifetimes to the task. Its light has been traveling through the void since before complex. Life existed on Earth long before our species had language, tools, or even awareness. And yet, that light eventually reached us. Not because the universe intended it to, but because the laws of physics allow it. And because, against all odds, we built instruments capable of noticing. As you move forward, you'll feel something strange happen. The numbers will get larger, the distances longer, the timescales deeper. But instead of feeling more informed, you may feel smaller. Not insignificant in a depressing way, but detached, as if your normal sense of place has been gently unplugged. That reaction is part of the experience. It's what happens when human intuition runs out of road. The mind looks for familiar reference points and finds none. That's when people often disengage, telling themselves the information is too abstract to matter. But if you stay with it, if you let go of the need to fully picture what's being described, something else emerges. You begin to understand that scale isn't just about size. It's about perspective. It's about realizing that the universe is under no obligation to fit inside the mental boxes we rely on to make sense of daily life. The largest galaxy ever discovered is proof of that. It exists at a level of magnitude that forces a quiet kind of humility, not because it diminishes us, but because it reveals how narrow our everyday framework really is. The shock isn't that something so big exists. The shock is that reality. was always capable of this, and we're only now beginning to glimpse it. What you're about to learn will challenge your sense of distance, time, and importance. Familiar benchmarks will crumble, comfortable scales will dissolve, and by the end, the Milky Way itself, the galaxy that contains every human who has ever lived, will feel less like a cosmic giant and more like a modest starting point. This is the edge of imagination, where understanding becomes abstract and where wonder begins to replace certainty. Stay here. Let the comparisons fail, because once they do, you'll be ready to grasp just how vast the universe truly allows itself to be. If you're already feeling a sense of strain trying to hold on to the scale of what we're discussing, that reaction is not a failure of intelligence. It's evidence that your brain is working exactly as it was designed to. Human perception did not evolve to understand galaxies, light years, or trillions of stars. It evolved to keep a fragile biological organism alive on a small, dangerous planet. Every instinct you have about distance, size, and time was shaped by survival pressures that rewarded speed and approximation, not precision or vastness. You needed to know how far a predator was, not how wide a spiral galaxy might be. You needed to judge whether food was a few steps away, not whether light could cross a region of space in 100,000 years. The universe we're about to explore exists far outside the scale your nervous system was ever meant to process. Your brain at certain ranges. It can intuitively grasp the difference between 1 and 10. With effort, it can stretch to hundreds or thousands. But once numbers climb beyond that, once we move into millions, billions, trillions, something subtle breaks. The numbers still register intellectually, but they stop carrying emotional weight. A million doesn't feel meaningfully different from a billion. A billion doesn't feel meaningfully different from a trillion. They all collapse into the same vague category of very large. This isn't because you're bad at math. It's because your mind has no lived experience to anchor those values. Without an anchor, meaning evaporates. Think about how you emotionally understand time. A minute feels different from an hour. An hour feels different from a day. A year feels different from a decade. But try to imagine a million years, or a billion. Your brain can repeat the words, but it cannot feel them. There's no internal clock calibrated to that scale. The same thing happens with distance. You can picture a kilometer. You can even picture the distance across a country. But when distances are measured in light years, the mental image stops forming. The concept becomes symbolic rather than experiential. This is where confusion creeps in, and many people quietly disengage, assuming the problem lies with them. It doesn't. The confusion is not a personal shortcoming. It's a universal human limitation. Every human who has ever lived shares this constraint, from ancient astronomers to modern physicists. Even scientists who work with these numbers daily don't feel them in the way they feel every day. Distances. They rely on equations, models, and analogies precisely because raw intuition fails. When professionals talk about cosmic scales, they're not accessing some hidden sense you lack. They're using intellectual scaffolding to compensate for the same perceptual gap you're experiencing now. Understanding this is important because it changes how you relate to what you're learning. Instead of trying to force your imagination to visualize the impossible, you can allow yourself to engage differently. You can stop demanding emotional clarity from numbers that were never meant to be felt. You can treat them as signposts pointing toward magnitude, not pictures meant to be seen. This shift builds trust not just in the information, but in yourself. You're not lost. You're standing at the edge of what human cognition can naturally do. There's also a deeper reason this matters. Our sense of importance, relevance, and meaning is tightly bound to scale. When things grow too large, they can feel irrelevant or alien. When distances stretch too far, events feel disconnected from our lives. By acknowledging the limits of perception, you remove the emotional barrier that often blocks curiosity. You're no longer asking, "Why can't I understand this?" You're asking, "How can I think about this in a way that respects my limits?" That question opens the door instead of closing it. So as the numbers grow larger from here, as distances stretch and timescales deepen, resist the urge to measure your understanding by how vividly you can imagine them. That's the wrong metric. Understanding at this level is quieter. It's about recognizing relationships, proportions, and implications, even when your inner picture remains blurry. Confusion doesn't mean failure. It means you've stepped beyond the environment your brain was shaped for, and that, in itself, is remarkable. Before everything stretches beyond recognition, it helps to stand on solid ground for a moment. Not metaphorically, but literally. Earth, a planet just over 12,000 kilometers wide. You know what that feels like, even if you've never circled it. You know what gravity feels like pulling you down. You know what a horizon looks like. How the sky curves overhead. How night replaces day with steady predictability. Earth is small enough to feel intimate, but large enough to feel complete. For most of human history, it was the entire universe anyone needed to understand. Now take a single step outward. The moon, roughly 400,000 kilometers away. Far enough that getting there took the combined effort of entire nations and decades of engineering. And yet, on a cosmic scale, that distance is almost nothing. Light takes just over a second to cross it. If Earth were the size of a basketball, the moon would be a tennis ball sitting a few meters away. Already, the emptiness between things is becoming apparent, but it still feels manageable. You can picture it. You can emotionally hold it. Pull back a little more and bring the sun into view. A star so massive that more than 1,000,000 Earths could fit inside it, yet still considered average by stellar standards. The sun sits about 150 million kilometers away, bathing our planet in energy that drives weather, life, and time itself. Light from the sun takes about 8 minutes to reach you. That delay is short enough to feel trivial, but long enough to remind you that space is not instantaneous. There is distance here. Real distance. Still, this too is familiar. You've seen diagrams, you've felt sunlight on your skin. The scale feels large, but not alien. Now expand your view to include the rest of the solar system. Mercury close in, racing around the sun. Venus wrapped in clouds. Mars cold and distant. Then, the giants. Jupiter with its swirling storms, Saturn with its impossible rings, Uranus and Neptune drifting in the dark. Beyond them, a vast halo of icy debris, comets, and forgotten remnants stretching outward far beyond the planets. Even here, the distances grow quickly. Neptune is so far away that sunlight takes more than 4 hours to reach it. Spacecraft take years to cross these gaps. But even now, your intuition is holding. The solar system feels like a big neighborhood. Empty, yes, but structured, ordered. Here's where anchoring matters, because what comes next builds on this foundation. If you shrink the solar system down so that Earth's orbit fits inside a coin, the nearest star would not be another coin. Nearby, it would be kilometers away. That's the first crack in everyday intuition. The space between stars is not crowded. It is vast beyond anything we encounter in daily life. Yet even this is still something you can intellectually track. One star, another star. Large gaps between them. Now imagine the solar system as a single point. Not the sun, not the planets, but everything humanity has ever known compressed into a dot. That dot orbits within a much larger structure, one that contains hundreds of billions of other dots just like it. This is where stability begins to give way, but not all at once. The Milky Way does not arrive as a shock. It unfolds gradually. A disk of stars about 100,000 light-years across, a number that already stretches meaning. Light, the fastest thing in the universe, taking 100,000 years to cross a single galaxy. Still, you can anchor it. It's big, but it has a shape. Arms, a center. A place where we live. What matters about starting here is not the numbers themselves, but the rhythm. Each step outward so far has preserved continuity. Earth to moon, moon to sun, sun to planets, planets to stars, stars to galaxy. At every stage, you're given something recognizable before being asked to accept something larger. This is how the mind stays oriented. Without this pacing, the next jump would feel like free fall. And that's exactly because even the Milky Way, vast as it is, still exists within a context your brain can partially manage. It's one object, one structure. You can talk about it as a whole. But beyond it lie distances and scales that no longer stack neatly. The contrast between what feels large now and what's about to be introduced is not linear. It's exponential. The stability you feel at this moment is intentional. It's the calm before scale becomes something different entirely. Hold on to this picture: Earth circling the sun drifting among nearby stars, those stars forming a vast, rotating galaxy. This is your last familiar map. Everything from here on will stretch that map until it no longer functions, until it becomes clear that the universe is not just bigger than you thought, but bigger than the tools you use to think at all. Now take that familiar map and let it expand until it begins to press against the limits of comprehension. The Milky Way is not just a backdrop of stars in the night sky. It is a vast, rotating system roughly 100,000 light-years from one edge to the other. That number alone deserves a pause. A light-year is the distance light travels in a single year, moving at nearly 300,000 kilometers every second. Multiply that by 100,000, and you are no longer dealing with a distance that can be pictured. You are dealing with a span so large that even the fastest thing in the universe requires 100 millennia to cross it. By the time a beam of light made the journey from one side of our galaxy to the other, modern humans would have risen, spread across the planet, and rewritten Earth's surface countless times over. Within that enormous disk live somewhere between 200 billion and 400 billion stars. Not planets, stars, suns. Each one a fusion reactor burning hydrogen into heavier elements. Many with their own planetary systems, moons, asteroids, and histories. Our sun is just one of them, located about 26,000 light-years from the galactic center in a relatively quiet region known as the Orion Arm. Even that placement is humbling. We are not near the edge, but not near the center either. We orbit in the suburbs of a structure so large that its core is hidden behind tens of thousands of light-years of intervening stars and dust. The motion within this system stretches intuition even further. The sun, along with everything bound to it, is racing around the galactic center at roughly 500,000 miles per hour. That sounds fast until you realize how vast the track is. At that speed, it still takes about 250 million years to complete a single orbit. One galactic year. Since the dinosaurs walked the Earth, our solar system has not even finished one full lap. The last time the sun was in roughly this position within the Milky Way. Complex life on Earth was only beginning to emerge in the oceans. Entire evolutionary eras unfold during what is, on a galactic clock, a single revolution. Human history barely registers against this backdrop. Recorded civilization spans perhaps 5,000 years. Agriculture, 10,000. Atomically modern humans, a few 100,000. All of it fits comfortably inside a fraction of 1% of a single orbit around the galaxy. When you compare the lifespan of empires, cultures, and even species to the slow, steady rotation of the Milky Way, the contrast is stark. What feels ancient to us is momentary at this scale. What feels permanent is fleeting, even the internal structure of the galaxy resists intuition. The space between stars is not crowded. On average, neighboring stars are separated by several light years. If you shrank the sun down to the size of a grain of sand, the nearest star would be another grain sitting miles away. Most of the galaxy is empty space, faint gas, and sparse dust spread across unimaginable volumes. And yet, when you look up from a dark location, you see a hazy band of light stretching across the sky. That glow is not a cloud. It is the combined light of billions upon billions of distant stars, stacked so densely along our line of sight that they blur together. Your eyes are registering a cross-section of the galaxy itself. For most of human history, that band of light was the universe. Cultures built myths around it, stories to explain its presence. It wasn't until telescopes revealed that the haze resolved into countless individual stars that anyone suspected the truth. And even then, the Milky Way was still thought to be everything. The idea that there could be other galaxies, each as large and complex as our own, was not widely accepted. Until the early 20th century, the realization that the Milky Way was just one among many fundamentally changed humanity's sense of scale. What makes this important is not just the raw size, but the realization that even this immense structure is already beyond what intuition handles comfortably. The Milky Way is big enough to dwarf human time, human history, and human relevance without effort. It operates on distances and durations that make civilizations feel like brief flickers. And yet, as overwhelming as it is, the Milky Way still sits within a category your mind can loosely grasp. It has a diameter, a star count, a center, a shape. You can talk about it as a single object. This is the last point at which that remains true. The Milky Way represents the upper edge of what feels conceptually manageable. Beyond it, scale stops adding and starts multiplying. Distances no longer stretch gently. They explode. Timescales no longer feel long. They become abstract. The all you feel here is real and justified, but it is also only a prelude. Because as vast as our galaxy is, as thoroughly as it overwhelms human intuition, it is not exceptional. It is not the upper limit. It is not even close. What comes next will make the Milky Way feel less like a cosmic giant and more like a familiar reference point you wish you could return to. For most of human history, the Milky Way was not just our galaxy. It was the universe itself. That faint, milky band stretching across the night sky seemed vast enough to contain everything that existed. Stars, myths, gods, destinies, all of it woven into that glowing river of light. When early astronomers turned their telescopes toward it and saw that the haze resolved into countless individual stars, the discovery felt enormous. The galaxy was far larger than anyone had imagined. But it was still singular. There was only one galaxy, one cosmic home. And for a long time, that idea felt unshakable. Then there were the smudges, faint, fuzzy patches of light scattered across the sky. Through early telescopes, they looked like clouds, neither sharp nor star-like. Astronomers cataloged them, named them, debated them. Some believed they were gas clouds within the Milky Way, places where new stars might be forming. Others, quietly, wondered if they were something else entirely. But the idea that they could be separate galaxies, entire island universes like our own, was too radical for most to accept. The distances involved seemed absurd. The implication that the Milky Way was not unique was deeply unsettling. This debate simmered for decades, growing more intense as telescopes improved, but answers remained elusive. Even among professionals, opinions hardened. The universe, many argued, simply wasn't big enough to contain countless galaxies. There was no need for such extravagance. Nature, after all, tended toward economy. To suggest otherwise felt like abandoning restraint. The Milky Way was already enormous beyond comprehension. Why multiply it? Why multiply it? The tending point in the early 20th century. Astronomers had better instruments, better data, and better questions. What they lacked was certainty. Some measurements suggested the smudges lay within our galaxy. Others hinted they were far beyond it. The disagreement wasn't about details. It was about the structure of reality itself. Either the Milky Way was everything, or it was just one piece of something vastly larger. There was no comfortable middle ground. When the evidence finally arrived, it didn't come gently. It arrived as a shock. Careful observations of specific stars revealed that these fuzzy objects were far too distant to belong to the Milky Way. They were millions of light-years away, well beyond the galaxy's edge. That meant they could not be clouds or clusters inside our own system. They had to be entire galaxies in their own right, each containing billions of stars. The universe didn't just grow. It exploded in scale overnight. The resistance didn't vanish instantly. Paradigms rarely collapse without friction. Accepting this new picture meant admitting that the Milky Way was not central, not special, not even particularly large by cosmic standards. It meant rewriting textbooks, abandoning cherished assumptions, and confronting a universe far more vast and indifferent than anyone had prepared for. The emotional weight of that realization matched its intellectual impact. Humanity's cosmic address had just been downgraded. What followed was a period of profound recalibration. If there were other galaxies, how many were there? How far did they extend? Did they cluster, collide, evolve? Every new question opened another door into the unknown. The universe was no longer a single grand structure with Earth tucked somewhere. Inside, it was an ocean filled with countless islands, stretching farther than imagination could reach. The Milky Way was not the universe. It was one example among many. This revelation marked a turning point in human thought. For the first time, scale itself became unstable. Distances once thought absurd were now merely large. Objects once considered unique were revealed as common. The sense of finality people had felt about the structure of the cosmos evaporated. There was always something beyond, always something larger, always another layer waiting to be uncovered. The shock wasn't just scientific, it was philosophical. Humanity had lost its last claim to cosmic centrality. Earth wasn't the center of the solar system. The solar system wasn't the center of the galaxy. And now, the galaxy wasn't the center of the universe. Each step outward stripped away another illusion of importance, replacing it with a deeper, colder, more honest picture of reality. And yet, this collapse of certainty did something unexpected. It didn't end curiosity, it intensified it. Once the idea of multiple galaxies became accepted, the question shifted from whether they existed to how extreme they could become. If the Milky Way was just one among many, then size was no longer bounded by familiarity. The universe had already proven it was capable of exceeding expectation. There was no reason to assume it would stop. Once the idea of multiple galaxies became unavoidable, another realization followed close behind. They were not all the same. The universe did not produce galaxies according to a single template. Instead, it built them in a staggering variety of sizes, shapes, and behaviors, each shaped by its own history. At first glance, this diversity seems orderly, even reassuring. Astronomers began grouping galaxies into categories, neat labels meant to bring structure to the chaos. But the more closely they looked, the more those categories blurred at the edges, revealing a universe far less constrained than anyone expected. At the smallest end of the scale are dwarf galaxies. These are the most common type in the universe. Yet they are almost invisible to casual observation. Many contain only a few billion stars, sometimes far fewer. Some are so faint and diffuse that they barely hold together at all. They orbit larger galaxies like loose companions, easily distorted, stretched, or even torn apart by gravity. In cosmic terms, they are fragile, but they are also ancient. Some dwarfs formed very early in the universe's history and still survive. Today, carrying clues about conditions shortly after the first stars ignited. They represent the lower bound of what we still comfortably call a galaxy. Move up the scale and you encounter spiral galaxies, the category most familiar to us. These are the classic pinwheel shapes, flat, rotating disks with sweeping arms rich in gas and dust. New stars are born in those arms, lighting them up with bright blue clusters and glowing nebulae. Spirals are dynamic systems, balanced delicately between rotation and gravity. They feel alive in a way other galaxies do not, constantly forming new generations of stars, even as older ones age and die. The Milky Way belongs to this group, which is why spirals often feel like the default or normal galaxy type. Then, there are elliptical galaxies. At first, they seem almost boring by comparison. No arms, no obvious structure. Just smooth, oval-shaped collections of stars, ranging from nearly spherical to stretched and elongated. But that simplicity is deceptive. Elliptical galaxies are typically enormous and ancient. Most of their stars are old, reddish, and long past their prime. Star formation has largely shut down. These galaxies are the end state of violence, the result of repeated mergers that have erased any delicate structure they once had. When spiral galaxies collide and combine, their ordered disks are scrambled, leaving behind a featureless swarm of stars moving in random orbits. Between these broad categories lie countless variations, irregular galaxies that fit no mold at all. Galaxies caught mid-collision, twisted into long tidal streams. Compact galaxies packed tightly with stars. Diffuse galaxies so spread out they appear almost empty. At first, this diversity suggests a kind of balance. Small galaxies here, medium galaxies there, large ones anchoring clusters, a cosmic ecosystem. With limits, but that sense of balance doesn't last long, because when astronomers began mapping galaxies more systematically, they noticed something unsettling. The distribution of galaxy sizes wasn't symmetrical. There wasn't a clean cutoff separating the biggest galaxies from everything else. Instead, there was a long, uneven tail stretching toward extremes. Most galaxies clustered around modest sizes. Many were small, some were large, and a tiny handful existed so far beyond the rest that they seemed almost out of place, like statistical errors that refuse to disappear. These outliers didn't just stretch the definition of large. They challenged the idea that there was a natural upper limit at all. Compared to dwarf galaxies, the Milky Way is already colossal. Compared to the Milky Way, some ellipticals are enormous. And compared to those, there are galaxies that sit in a category of their own, not because they break a rule, but because the rules never included them in the first place. They exist at the far end of the scale hierarchy, where bigger stops being a useful descriptor and starts to feel like understatement. What makes this hierarchy so compelling is that it hints at a process rather than a design. Galaxies are not assigned a size at birth and left that way. They grow. They merge. They consume. Small galaxies fall into larger ones. Medium galaxies collide and combine. Over billions of years, gravity favors accumulation. The rich get richer. The massive become more massive. And in certain environments, especially the dense centers of galaxy clusters, this process can run nearly unchecked. This answers a quiet question in the mind. If galaxies can grow through merger after merger, if size is not fixed but accumulated, then how far can that process go? Is there a practical ceiling, or only a temporary one defined by circumstance? The universe has already shown a willingness to exceed expectation at every scale we've examined. There is no obvious reason it would suddenly stop just short of the unimaginable dot at this stage. Curiosity begins to sharpen. The familiar categories still exist, but they feel provisional, like signposts rather than boundaries. You can sense that somewhere out there, among the countless galaxies scattered across the observable universe, there must be examples that stretch this hierarchy to its breaking point. Objects that make even giant ellipticals seem modest. Galaxies that didn't just grow large, but grew relentlessly, fed by their environment over cosmic time. The important shift here is subtle. We move from thinking in terms of typical galaxies to thinking about extremes, not averages, but exceptions. Not what is common, but what is possible. Once that shift happens, anticipation takes over. If the universe allows for galaxies far outside the normal range, then the question is no longer whether such giants exist, but what they are like, how they formed, and just how far beyond normal they really go by the time astronomers began to fully appreciate the diversity of galaxies. Another, quieter realization was taking shape beneath the data. The categories that once felt so useful to dwarf, spiral, elliptical, were starting to look less like firm definitions and more like rough conveniences. They worked well for the majority. They described what was common, but scattered through. The observations were objects that didn't sit comfortably anywhere. Galaxies that were technically elliptical, yet so vast that the label felt insufficient. Systems so extended, so massive, that calling them large barely hinted at the truth. At first, these objects didn't stand out dramatically. They were distant, faint, and difficult to study in detail. Many sat at the centers of dense galaxy clusters, surrounded by hundreds or thousands of smaller companions. Against that crowded background, their true scale was easy to miss. Their outer regions faded gradually into space, with no sharp boundary to announce where the galaxy ended and intergalactic darkness began. Early measurements underestimated them, treating them as oversized but otherwise ordinary ellipticals. It took time, patience, and better instruments for the full picture to emerge. As observations improved, something unsettling became clear. These galaxies were not just slightly bigger than normal. They were orders of magnitude larger in ways that broke intuitive expectations. Their stellar halos extended hundreds of thousands, sometimes millions, of light years beyond their bright cores. Their gravitational influence dominated entire clusters. They contained not just billions of stars, but tens of trillions. At this point, the usual mental yardsticks stopped working. Comparing them to the Milky Way no longer felt like a meaningful exercise. The gap was too wide. What made this especially disorienting was how quietly these giants existed. There was no dramatic visual cue announcing their extremity. No single image that instantly conveyed their dominance. Unlike a massive star or a blazing quasar, their power wasn't expressed through brightness or violence. It was expressed through scale, through sheer, patient accumulation. They were not spectacular in the way explosions are spectacular. They were overwhelming in the way continents are overwhelming, too large to grasp all at once. As astronomers began mapping galaxy clusters in more detail, a pattern emerged. The largest of these extreme galaxies almost always sat at the very centers of clusters, like gravitational anchors. Around them, smaller galaxies orbited, interacted, and, over time, often disappeared. Their stars were stripped away and added to the growing halo of the central giant. This process wasn't rare or unusual. It was simply slow. so slow that its consequences only became obvious when viewed across billions of years. The implication was unsettling. If galaxies could grow by consuming others, if some galaxies had been sitting in the perfect environment to do so for most of cosmic history, and there was no simple reason they couldn't grow to truly absurd sizes. Not infinite, perhaps, but far beyond anything that felt reasonable. The universe, once again, was revealing that it had no interest in staying within the boundaries humans found comfortable. At this stage, scientists faced a subtle problem. Language began to fail. How do you describe something that is not just the largest example of a category, but so extreme that it stretches the category itself? Calling these galaxies giant ellipticals was technically correct, but emotionally misleading. The phrase suggested something like the Milky Way, only bigger. In reality, the difference was not a matter of degree, it was a matter of kind. These objects lived at the far end of a scale most people didn't even realize existed. As measurements refined further, the numbers started to carry a kind of quiet menace. Diameters measured not in tens or hundreds of thousands of light years, but in millions. Star counts that made the Milky Way's hundreds of billions feel almost quaint. Central black holes whose masses dwarfed anything seen in more familiar galaxies. Each new data point pushed the sense of escalation higher while still refusing to deliver a clean emotional payoff. You could understand the numbers, but you couldn't feel them. And perhaps most unsettling of all was the realization that these giants were not anomalies in the sense of being mistakes. They followed the same physical laws as everything else. Gravity behaved normally. Stars aged normally. Mergers occurred normally. There was no exotic physics required to explain them. They were simply the end result of ordinary processes given enough time, enough material, and the right environment. That made them harder to dismiss. If the universe could produce structures like this naturally, then the question was no longer whether such extremes should exist, but why we had ever expected moderation in the first place. At this point in the story, anticipation begins to tighten. You can feel that the scale hierarchy is nearing its peak. We've moved from small galaxies to large ones, from typical giants to extreme outliers. The trend is unmistakable. Each step upward has not just added size, but widened the gap between expectation and reality. The next step cannot be modest. It cannot simply be a bit bigger. It must represent something close to a limit, at least as far as we currently know. Yet the name of this object, the specific identity of the largest known galaxy, remains withheld for a reason. Names can be grounding. They make things feel manageable, cataloged, understood. What matters here is not the label, but the approach. The slow realization that such a galaxy exists at all. That somewhere in the observable universe, there is a structure so vast that it dwarfs not only our home galaxy, but most others by an almost absurd margin. There is also a growing emotional tension beneath the facts. Because if the Milky Way already made human history feel small, and if these extreme galaxies make the Milky Way feel modest, then confronting the largest of them threatens to sever the last intuitive connection entirely. We are approaching a scale where even the language of galaxy feels inadequate, where the object in question begins to resemble a region of the universe rather than a single thing. This is the edge of escalation. The point where curiosity is mixed with apprehension. You sense that once the reveal happens, there will be no easy way to reframe it back into familiar terms. The numbers will not just grow larger. They will cross into a range where imagination fully disengages, leaving only acceptance behind. And when that moment arrives, when the largest known galaxy finally steps into focus, it will not feel like the discovery of another object. It will feel like discovering that the universe has been playing a much bigger game than we ever suspected, quietly assembling structures so vast that even our boldest ideas about scale were never ambitious enough to prepare us. The galaxy escalation does not have a poetic name. It does not sound mythic or dramatic. It is known simply as IC 1101, a label pulled from an old astronomical catalog, assigned long before anyone understood what it truly was. That plainness is almost fitting because nothing about its name prepares you for what it represents. IC 1101 sits more than 1 billion light-years away from Earth, buried deep in the heart of a massive galaxy cluster called Able 2029, in the direction of the Virgo constellation. From our perspective, it is a faint, distant smudge, barely distinguishable from the countless other galaxies scattered across the sky. For most of human history, and even for much of modern astronomy, it was simply overlooked. The reason it remained hidden for so long has nothing to do with secrecy or rarity. It is not concealed behind cosmic dust or masked by exotic physics. It was hidden by scale itself. IC 1101 is so large that its outer regions are extraordinarily faint, spread thinly across space rather than packed into a bright, obvious structure. Telescopes are naturally drawn to concentrated light, dense stars, bright cores, sharp edges. IC 1101 offers none of those visual cues. Its stars are dispersed across an immense volume, fading gradually into intergalactic darkness with no clear boundary to announce where the galaxy truly ends. For decades, astronomers saw only its central region and assumed that was most of what there was. When early surveys cataloged IC 1101, it appeared unremarkable, at least relative to other large, elliptical galaxies. It was known to be massive, but not extraordinary. The tools of the time simply weren't sensitive enough to detect the full extent of its stellar halo. Its true size was hiding in plain sight, not because it was too small to see, but because it was too spread out to stand out. This is one of the great ironies of cosmic discovery. Some of the largest things in the universe are the hardest to recognize as observational techniques improved. Astronomers began to notice that IC 1101 behaved differently from typical galaxies. Measurements of its gravitational influence suggested far more mass than its visible core could explain. Its interaction with surrounding galaxies hinted at a dominant presence within the cluster. Slowly, piece by piece, evidence accumulated that something was being missed. Deeper imaging revealed faint streams of stars extending far beyond the galaxy's previously assumed edge. Each new observation pushed that edge farther out. Eventually, the realization became unavoidable. IC 1101 was not merely large, it was immense on a scale that strained existing categories. Its diameter was estimated to lie somewhere between 4 and 6 million light-years. To put that into perspective, the Milky Way spans about 100,000 light-years. IC 1101 is roughly 50 times larger from end to end. If it replaced our home galaxy, it would not only engulf the Milky Way, but also swallow neighboring galaxies entirely, including Andromeda and Triangulum, folding whole galactic systems into its vast structure. This sheer size is why its location matters. IC 1101 sits at the gravitational center of Able 2029, a rich galaxy cluster containing hundreds of galaxies bound together by gravity. In such an environment, growth is almost inevitable. Smaller galaxies drift inward over billions of years, pulled toward the center where the gravitational well is deepest. When they arrive, they are torn apart, their stars stripped and added to the growing halo of the central giant. IC 1101 has spent most of cosmic history in the perfect position to grow without restraint. Its distance from us also played a role. In delaying recognition, at more than 1 billion light-years away, we are not seeing IC 1101 as it exists today, but as it was when complex life on Earth had barely begun to diversify. Its light has been traveling through space for longer than multicellular organisms have existed on this planet. That immense distance makes precise measurement difficult. Determining size, mass, and structure at such scales requires careful modeling and indirect inference. Not simple observation. What makes the discovery of IC 1101 so compelling is not just that it is the largest known galaxy, but that nothing about its existence violates the laws of physics. It did not require new theories or exotic matter to explain. It emerged naturally from processes we already understand: gravity, merger, accumulation, time. Given enough material and enough patience, the universe simply kept building. IC 1101 is the result of that patience stretched across billions of years. In that sense, its discovery is both a resolution and a warning. It resolves the question of how large galaxies can become, at least for now. But it also warns us against assuming we have reached the final answer. IC 1101 was not hiding because it was rare. It was hiding because our expectations were too small to understand the diameter of this galaxy. The first thing that has to happen is a kind of surrender. Normal comparison is not going to survive the process intact. But we can still walk toward it, step by step, letting each layer overwhelm the last, until intuition finally gives up and abstraction takes over. Start again with the Milky Way, because it is the largest structure most people ever learn to treat as a single object. From one edge to the other, our galaxy spans roughly 100,000 light-years. Light, moving at the fastest speed the universe allows, needs 100 millennia to cross it. That distance already dwarfs all of human history, all recorded memory, all civilization combined. When we say the Milky Way is vast, we are not exaggerating. It is an island of stars so large that its internal distances make entire species rise and fall during a single crossing. Now imagine placing the Milky Way next to IC 1101, not merging them, not interacting them, just setting them side by side. For scale, the Milky Way would not stretch meaningfully across IC 1101's disk. It would sit inside it like a coin dropped onto a frozen lake. You could line up 40 to 60 Milky Ways end to end before you reached the far side of this galaxy. And that is not poetic language. That is literal geometry. Our entire galaxy, with all its spiral arms, star-forming regions, and billions of suns, would occupy a small fraction of the larger structure. That comparison alone tends to break intuition. But it gets worse when you widen the frame. The Milky Way is not alone. It has neighbors. The Andromeda Galaxy lies about 2.5 million light-years away and is, itself, slightly larger than the Milky Way. Between them is a gulf of space so vast that even at the speed of light, it takes millions of years to cross. That distance feels enormous when discussed on its own. It defines the scale of galaxy-to-galaxy separation. But IC 1101 does not merely reach toward Andromeda. Its estimated diameter is so large that, if placed where our galaxy is, Andromeda would sit comfortably inside its outer regions. The space that currently separates two major galaxies would become interior real estate. Extend that thought further. The Triangulum Galaxy, another member of our local group, would also be swallowed. So would the large and small Magellanic Clouds. Dozens of dwarf galaxies that orbit the Milky Way would not register as separate systems at all. They would become minor density fluctuations within a much larger whole. What we currently think of as a galactic neighborhood would collapse into a single structure. Not because those galaxies changed, but because the frame of reference did. At this point, individual galaxies starts to feel inadequate. So shift scale again. Galaxy clusters are vast collections of hundreds or thousands of galaxies bound together by gravity. They stretch across tens of millions of light-years. Within them, galaxies orbit, interact, merge, and evolve over billions of years. Normally, a single galaxy, even a large one, occupies only a small fraction of a cluster's volume. But IC 1101 is not a typical member. It sits at the center of its cluster like a gravitational continent. Its stellar halo extends so far outward that it begins to blur the distinction between galaxy and cluster core. There is no sharp line where one ends and the other begins. Instead, stars simply thin out, fading gradually into intergalactic space. Now consider the number itself. 4 to 6 million light-years. Saying it once does nothing. Saying it twice does nothing. The number refuses to cooperate emotionally. So convert it into time. Light leaving one edge of IC 1101 would still be traveling when the first human ancestors stood upright. It would still be traveling when agriculture began. It would still be traveling when the pyramids were built, when Rome rose and fell, when telescopes were invented, when radio waves first leaked into space. It would only now be reaching the other side, and that journey assumes uninterrupted motion. At the maximum speed the universe allows, try a different approach. Imagine shrinking distances instead of expanding them. If the Milky Way were reduced to the size of a dinner plate, IC 1101 would span something closer to a large swimming pool. Not a slightly bigger plate, not a table, a pool. The difference is no longer incremental, it is architectural. One object belongs in a kitchen. The other reshapes a landscape. Even this analogy falls short because it suggests boundaries that don't really exist. IC 1101 does not have crisp edges. Its outer stars are so sparsely distributed that defining where the galaxy ends becomes a matter of convention, rather than observation. Astronomers must decide how faint is to faint, how diffuse is to diffuse, before drawing a line. Change that threshold, and the galaxy grows larger still. In this sense, its size is not just immense, but slippery. It resists containment even. In definition, now bring gravity into the picture. A structure this large does not merely occupy space, it dominates it. The gravitational influence of IC 1101 extends across a vast region, shaping the motions of surrounding galaxies and hot gas. Objects tens of millions of light-years away feel its presence indirectly through the cluster it anchors. The galaxy is not just something you measure across. It is something you orbit around, something that organizes matter on a scale normally reserved for collections of galaxies rather than individual ones. At some point in this escalation, a subtle shift happens. You stop trying to visualize the whole thing. The mind quietly abandons the effort. What remains is not an image, but an understanding of relationship. You understand that the Milky Way is small by comparison. You understand that distances between galaxies are no longer meaningful separators here. You understand that this object occupies a tier of scale that makes previous categories feel provisional. The galaxy becomes less like a thing and more like a region, a domain of space defined by shared history and gravity rather than neat boundaries. This is where awe-stacking reaches its peak. Each comparison has not replaced the last, but layered on top of it. Milky Way inside IC 1101. Neighboring galaxies inside IC 1101. Local group inside IC 1101. Familiar cosmic distances turned inward. The result is not clarity, but reverence. A recognition that the universe is capable of assembling structures so vast that even our best comparative tools collapse under their own weight. And perhaps the most unsettling part is this. IC 1101 is not theoretical. It is not hypothetical. It is not a simulation or an extrapolation. It is there, right now. Its light is reaching us after a journey of more than 1 billion years. The scale you are struggling to process is not an abstract possibility. It is an existing fact of the universe. One of many when astronomers estimate the number of stars in this galaxy. They arrive at a figure so large that it immediately stops behaving like information. Roughly 100 trillion stars. Written out, the number looks impressive. Spoken aloud, It sounds dramatic, but emotionally, it lands with a dull thud. 100 trillion does not feel meaningfully different from 10 trillion or a trillion. It simply registers as too many. That reaction is not indifference. It is a cognitive defense. The mind recognizes that it has no framework for such a quantity and quietly disengage. To understand why this happens, it helps to think about how humans normally relate to numbers. You can feel the difference between 1 and 10. You can feel the difference between 10 and 100. Even 1,000 still carries weight. But once numbers climb into the millions, they lose texture. 1,000,000 seconds is about 11 days. 1,000,000,000 seconds is more than 30 years. Intellectually, that difference is enormous. Emotionally, it barely registers unless you stop and translate it into lived experience. Star counts at the scale of this galaxy skip past those thresholds entirely. They leap straight into abstraction. So instead of trying to picture 100 trillion individual suns scattered through space, consider time. Imagine you begin counting stars at a steady pace, 1 star per second. No pauses, no breaks, no sleep. You start at the moment the first pyramids are being planned. You keep counting through the rise and fall of every ancient civilization. You continue through the entire span of recorded history, through the invention of writing, the printing press, electricity, computers, spaceflight. After all of that, after every moment of human civilization has passed, you are still nowhere near finished. Counting to 100 trillion at 1 star per second would take more than 3 million years. That is not a metaphor. That is a calculation. Now try to feel what 3 million years actually means. Modern humans have existed for perhaps 300,000 years. 3 million years is 10 times longer than the entire history of our species. It predates language, culture, art, and agriculture. It reaches back to a time when our ancestors were barely distinguishable from other early hominins. And that span of time, 10 human histories end to end, would be required just to name each star once, assuming the impossible condition that you never stop counting. If you speed up the process, the result is still unsettling. Suppose you count 1,000 stars per second. At that pace, you would still need more than 3,000 years. That is longer than all recorded history. Longer than the lifespan of most civilizations. Longer than the gap between the Bronze Age and the modern world. The number refuses to compress into something manageable, no matter how aggressively you approach it. This is why this scale don't feel real. They exist outside emotional calibration. Your brain is not meant to track collections of objects that would take longer than civilizations to enumerate. And yet, every one of those stars, it is real. Each has mass. Each produces energy. Many have planets. Many have histories stretching back billions of years. The galaxy is not a smooth glow. It is a population, a vast one. What makes this even more difficult to internalize is that stars are not packed closely together. The average distance between them remains immense. This means that 100 trillion stars does not translate to a bright, crowded interior. It translates to a colossal volume of mostly empty space, lightly populated by suns drifting in slow gravitational choreography. The galaxy's enormity is not just about quantity, but about distribution. The stars are spread thinly across millions of light years, forming a structure whose density would feel almost empty. If you could stand inside it, there is also a deceptive calm to such numbers. 100 trillion stars sounds static, as if it were a frozen count. In reality, it represents a dynamic system. Stars are aging, dying, colliding, and drifting. Some have already burned out. Others are still forming from the remnants of past mergers. The number itself is an estimate, Snapshot of an ongoing process that unfolds over cosmic time. Even the act of counting is a simplification imposed on something far more fluid. At this point, the mind often tries to retreat to comparison again. Our galaxy has hundreds of billions of stars. That already feels like too many. But the jump from hundreds of billions to 100 trillion is not intuitive. It is not additive. It is multiplicative. The Milky Way does not feel slightly smaller by comparison. It feels categorically different. What once seemed vast becomes a reference point rather than a contender. This is where memory imprinting occurs. You may not remember the exact number. Later, you may forget whether it was 80 trillion or 100 trillion. But you will remember the feeling that the number produced, the sense that counting breaks. That time itself becomes the unit of comparison. That a single galaxy can contain more stars than human history can emotionally process. And that realization lingers. Because once you accept that one galaxy can hold 100 trillion suns, the universe no longer feels like a collection of objects you might someday catalog. It feels like something fundamentally beyond enumeration. Not infinite, perhaps, but vast enough that the difference no longer matters. To understand how a galaxy can grow to such an extreme size, you have to let go of the idea that galaxies are born large. They aren't. The universe does not create giants in a single act. It builds them slowly, patiently, through a process that is at once destructive and generative. The largest galaxies are not monuments of peaceful growth. They are the accumulated aftermath of billions of years of collision, disruption, and gravitational violence. And paradoxically, is this chaos that gives rise to the most massive and stable structures we observe. In the early universe, shortly after the first atoms formed, matter was distributed unevenly. Tiny fluctuations in density meant that some regions had slightly more mass than others. Gravity amplified those differences. Regions with more matter pulled in even more, growing denser over time. The first galaxies were small, primitive systems composed of gas collapsing into the earliest stars. These initial galaxies were nothing like the giants we see today. They were fragile, irregular, and short-lived by modern standards. But they were the seeds. As time passed, gravity began to connect these seeds. Galaxies did not form in isolation. They formed in neighborhoods, drawn together by mutual attraction. When two galaxies approached each other, they didn't simply bounce apart. Their stars passed through one another, but their gravitational fields interacted deeply. Orbits were distorted. Gas clouds were compressed. Tidal forces stretched each galaxy into long streams of stars. Over millions of years, these interactions drained energy from their motion, causing the galaxies to spiral closer together until they merged into a single, larger system. This process is known as hierarchical structure formation, and it underlies nearly everything we see on the largest cosmic scales. Small structures form first, then they combine to make larger ones. Those larger structures merge again to make even larger ones. There is no final blueprint. There is only accumulation. The universe builds upward, not by design, but by inevitability. Gravity has a simple rule: where mass gathers, more mass will follow. What's important to understand is that these mergers are not rare events. Over billions of years, they are the norm. A galaxy like the Milky Way has already absorbed numerous smaller galaxies. We can still see the evidence in faint streams of stars wrapping around our galaxy, remnants of systems that once existed independently. These mergers are not clean. They are messy, prolonged, and transformative. And when they happen repeatedly, they erase structure. Spiral galaxies, with their elegant arms and rotating disks, are particularly vulnerable to this process. Their beauty depends on order. When two large spirals collide, that order cannot survive. The collision scrambles stellar. orbits, heats gas, and destroys the disk. What emerges is not another spiral, but a swollen, rounded cloud of stars moving in random directions. This is how elliptical galaxies are born. They are not primitive. They are the survivors of repeated upheaval. Now imagine this process playing out not once or twice, but dozens of times in the densest regions of the universe. In the centers of massive galaxy clusters, hundreds or thousands of galaxies orbit within a shared gravitational well. The central region of such a cluster is a feeding ground. Smaller galaxies lose energy through interactions and slowly drift inward. When they get too close to the central giant, they are torn apart. Their stars are stripped and added to the growing halo. Their gas is heated or expelled. Their identity is erased. Over billions of years, this creates a runaway effect. The largest galaxy grows larger simply because it is already large. Its gravity makes it more likely to capture others. Each merger increases its mass, which increases its gravitational reach, which makes future mergers even more likely. This is not a balance, it is a feedback loop. And in the right environment, with enough time, that loop can produce something extraordinary. What makes this process unsettling is how ordinary it is. There is no single catastrophic moment where a galaxy suddenly becomes enormous. There is no cosmic switch that flips. Growth happens incrementally, quietly, often invisibly. A dwarf galaxy disappears here. A spiral is absorbed there. Stars are added one stream at a time. Over millions of years, nothing seems dramatic. Over billions, the result is staggering. Violence is the engine, but not the spectacle. Stars rarely collide directly. The scale is too large, the distances too vast. The violence is gravitational. It is expressed through distortion, heating, and disruption. It reshapes galaxies without destroying their components, and from that reshaping comes stability. The largest elliptical galaxies are often dynamically. Their stars move in predictable statistical patterns. The chaos that formed them has settled into equilibrium. This is the counterintuitive beauty of the process. Destruction creates order. Mergers erase delicate structures, but they also produce massive, long-lived systems. The more violent the history, the smoother the result. A giant elliptical galaxy is not chaotic because it experienced chaos. It is smooth because it survived so much of it. Scientific authority reinforces this picture not through speculation, but through observation and simulation. Computer models of cosmic evolution built from well-tested physical laws consistently reproduce this hierarchy. When you let gravity operate over billions of years in a universe like ours, large galaxies emerge naturally. When you place them at the centers of clusters, they grow disproportionately large. No exotic assumptions are required. The universe behaves exactly as the equations predict. This is what makes the largest galaxies so powerful as evidence. They are not anomalies that break the rules. They are confirmations of them. They show us what gravity does when given enough time and enough material. They show us that the universe is not gentle, but it is consistent. It builds not by avoiding destruction, but by incorporating it. And once you understand this, the existence of a galaxy as large as the biggest one we've discovered no longer feels impossible. It feels inevitable. Given billions of years, dense environments, and the relentless pull of gravity, something like this was bound to form somewhere. The shock is not that it exists. The shock is that we ever expected the universe to stop short of such extremes. If you see and simulations and look at this galaxy through the lens of story, a different image emerges. Not a peaceful island of stars drifting quietly through space, but a survivor. A dominant presence shaped by hunger, patience, and time. IC 1101 did not become what it is by chance. It became what it is by feeding. For billions of years, this galaxy has occupied the most advantageous position imaginable, the gravitational center of a crowded galaxy cluster. In that role, it behaves less like a passive object and more like a cosmic predator. Smaller galaxies wander too close, slowed by countless subtle interactions with their neighbors. And once they cross a certain threshold, escape becomes impossible. Gravity does the rest. The victim stretches, distorts, and begins to unravel. Stars are pulled free, streams form, identities dissolve. What was once a distinct galaxy becomes raw material. This process is not fast. There is no sudden snap, no single moment of destruction. A galaxy might take hundreds of millions of years to fully disappear. From a distance, it would look almost gentle. Two systems overlapping, stars passing harmlessly through one another. Nothing exploding, nothing colliding directly. Beneath that calm surface, the outcome is already decided. The smaller galaxy loses coherence. Its stars are redistributed. Its history is erased. And IC 1101 grows, almost imperceptibly, but relentlessly. Over time, this has happened again and again. Not once, not twice, dozens of times. Major mergers with substantial galaxies, each one contributing billions or trillions of stars. Countless smaller mergers with dwarf galaxies that barely registered as meals at all. Each encounter left a mark, not as a scar, but as added mass, added reach, added dominance. The galaxy we see today is not a single structure born whole, but a composite, assembled piece by piece from the remains of others. Thinking of this in abstract terms makes it feel distant, clinical. But when you imagine the process unfolding across deep time, it takes on a darker, more visceral character. Picture a galaxy drifting through the cluster, its stars bound together by gravity, its internal rhythms stable. Slowly, its orbit decays. Each pass near the cluster's center robs it of energy. IC 1101 looms larger in its sky. Tidal forces stretch it, pulling stars outward like loose threads. Gas is stripped away, starving it of the fuel needed to form new stars. Eventually, there is nothing left to resist. The galaxy is no longer itself. It has been absorbed. From IC 1101's perspective, this is not violence. It is inevitability. Gravity does not intend harm. It simply follows gradients. But the outcome is the same as predation. One entity grows stronger at the expense of others. One identity persists by incorporating many. Over billions of years, this dynamic produces a single enormous presence surrounded by absence. Where there were once many galaxies, there is now one dominant core and a halo of borrowed stars. This predator metaphor resonates because it gives emotional shape to an otherwise abstract process. You begin to see IC 1101 not as a static object, but as a character with a history. A being forged by environment and opportunity. In a quieter corner of the universe, it might have remained an ordinary elliptical galaxy, but placed at the center of a rich cluster with a steady supply of incoming material, it became something else entirely. Size was not its goal. It was the consequence of survival in a crowded cosmic ecosystem. What makes this story unsettling is that the galaxy is not finished. Its growth has slowed, but it has not truly stopped. As long as smaller galaxies continue to drift inward, as long as gravity continues to operate, the process continues. Even now, stars are being added to its outer halo, one faint stream at a time. Each addition is subtle, almost invisible, but together they define the galaxy's true scale. There is also a quiet irony here. By consuming so many others, IC 1101 has made itself strangely uniform. The more galaxies it absorbed, the more its internal structure was smoothed out. Spiral arms vanished. Star-forming regions disappeared. What remains is a vast, featureless glow, an object whose violent past is written not in sharp edges, but in absence. The predator no longer looks fierce. It looks ancient, calm, satiated. And yet, knowing its history changes how you see it. That smoothness is not simplicity. It is the end result of countless acts of cosmic cannibalism layered on top of one another. Each star in its halo may once have belonged to a different galaxy, orbiting a different center, following a different history. Now they move together, bound into a single gravitational identity. This is what engagement through character accomplishes. The galaxy stops being just a number or a diagram. It becomes a story of accumulation, dominance, and time. A reminder that the largest structures in the universe are not built through gentle assembly, but through relentless interaction. IC 1101 is not monstrous because it is evil or intentional. It is monstrous because gravity, given enough time and opportunity, always favors the biggest consumer in the room. Seen this way, the galaxy is less a marvel and more a warning about scale itself. Growth does not require ambition. It requires position, patience, and physics. And once those conditions are met, even something as unimaginably vast as the largest known galaxy begins to feel like a natural outcome of a universe that never stops. Pulling things together, there is a quiet irony at the heart of the largest galaxy we've ever discovered. After billions of years of growth, after consuming dozens of other galaxies and accumulating more stars than most minds can process, it is no longer doing the very thing galaxies are most famous for. It is not actively forming stars. In a universe where size often suggests power and activity, this giant has entered a long, slow stagnation. It is immense, dominant, and yet, in a very real sense, past its prime. To understand why, you have to think about what star formation actually requires. Stars are born from cold gas. Vast clouds of hydrogen collapse under gravity, heat up, and ignite nuclear fusion. This process depends on having large reserves of gas that are cool enough to clump together. Spiral galaxies like the Milky Way still have plenty of this raw material. Their disks are rich in gas and dust, constantly recycling matter into new generations of stars. That ongoing birth is what gives spirals their bright blue arms and sense of vitality. The largest galaxies, however, tell a different story. IC 1101 is classified as an elliptical galaxy, and ellipticals are, by their nature, old. They are dominated by red and yellow stars that formed billions of years ago and have been slowly aging ever since. The reason is not mysterious. It is a consequence of how these galaxies grew. Every time IC 1101 consumed another galaxy, it didn't just add stars to its body. It also disrupted and depleted the gas that makes new stars possible. Galaxies are violent in subtle ways. When two galaxies collide, their gas clouds slam into each other, heating up to extreme temperatures. Hot gas resists collapse. Instead of forming new stars, it expands, sometimes escaping the galaxy's gravitational grip entirely. In other cases, mergers trigger brief, intense bursts of star formation that rapidly use up available gas in a cosmic flash of activity. Either way, the long-term result is the same. The fuel runs out. Over billions of years and dozens of mergers, IC 1101 has effectively exhausted its supply. What little gas remains is often too hot, too diffuse, or too disturbed to settle into the dense clouds required for star birth. The galaxy has become a graveyard of stars rather than a nursery. Its light is steady and subdued, dominated by ancient suns that will continue to shine quietly for billions of years, but without replacement when they finally burn out. This creates a stark contrast. On one hand, IC 1101 is the largest known galaxy, stretching across millions of light years and containing around 100 trillion stars. On the other hand, it is no longer growing in the way that feels creative or dynamic. Its size represents accumulation, not renewal. It is a monument built from past activity, not a site of ongoing construction. The processes that made it enormous have also ensured that it will never again be young. There is a melancholy to this realization. We tend to associate growth with life and size with vitality. But in the universe, extreme size often signals the opposite. It marks the endpoint of a long evolutionary road. The biggest galaxies are not bustling hubs of creation. They are settled, mature systems that have already experienced their most dramatic moments. Their future is not explosive, but quiet. This stagnation is also tied to another force: entropy. Over time, systems tend to move toward states of equilibrium. Energy spreads out, differences smooth away. In IC 1101, repeated mergers have randomized stellar orbits, erased structure, and eliminated the conditions needed for sustained star formation. The galaxy has reached a kind of thermal and dynamical balance. Nothing dramatic happens anymore, because there is no easy way for it to happen. Even the galaxy's immense gravity, once a tool for growth, now contributes to its stillness. Gas falling into the center can be heated by energetic processes around the central black hole, preventing it from cooling and collapsing. In this way, the very mass that defines the galaxy helps suppress future creation. Power becomes self-limiting. The giant holds itself in check. What you're left with is a paradox that feels deeply human. The galaxy achieved unimaginable scale through relentless accumulation, only to arrive at a state where change slows to a crawl. It is not dying in any immediate sense. Its stars will continue to shine for billions of years. But it is no longer becoming anything new. The story of growth has ended. The story of endurance has begun. This contrast reframes how we think about cosmic success. IC 1101 did not win by becoming large. It simply followed gravity to its logical conclusion. And that conclusion is not eternal expansion, but eventual stillness. The universe allows things to grow to extraordinary extremes, but it also imposes limits. Once resources are consumed and energy is spread thin, even the largest structures settle into quiet decline. In that sense, the largest galaxy is not a symbol of infinite possibility. It is a reminder of impermanence on the grandest scale. Size does not guarantee vitality. Dominance does not ensure renewal. Even a galaxy that dwarfs all others we know is subject to the same slow drift toward equilibrium. Its vastness is real, but so is its silence. At the very center of IC 1101 lies something even more extreme than the galaxy itself. Hidden beneath the smooth glow of hundreds of trillions of stars is an object so massive, so dense, and so dominant that it reshapes the behavior of everything around it. A supermassive black hole, not merely large by human standards, but one of the largest ever inferred anywhere in the observable universe. Every large galaxy hosts a black hole at its core. This is not an exception. Our own Milky Way contains one, with a mass about 4 million times that of the Sun. That number already sounds enormous, yet it remains modest by cosmic standards. In IC 1101, astronomers estimate that the central black hole weighs somewhere between 40 billion and 100 billion times the mass of the Sun, not millions, billions. A single object containing more mass than tens of thousands of Milky Way-sized black holes combine numbers like that immediately resists comprehension. So scale has to be rebuilt carefully. The mass of a black hole determines the size of its event horizon, the invisible boundary beyond which nothing can escape. For a black hole as massive as the one at IC 1101's center, That boundary would extend roughly 150 billion kilometers from the core. To put that into perspective, the entire solar system, from the Sun to the orbit of Neptune, spans about 9 billion kilometers. This black hole's event horizon alone would engulf our entire planetary system many times over. If it replaced our Sun, the boundary where light itself becomes trapped would stretch far beyond Pluto, swallowing everything we consider home. And yet, even that description is misleading in a subtle way. Black holes are not solid objects. They do not have surfaces in the way planets or stars do. Their mass is compressed into a region of spacetime so warped that normal ideas of distance and direction stop applying. The event horizon is not a physical shell. It is a mathematical boundary, a point of no return defined by gravity's absolute dominance. Crossing it does not feel like hitting a wall. It feels like falling into inevitability. What makes this black hole truly unsettling is not just its size, but how quietly it exerts its influence. Despite containing tens of billions of solar masses, it does not behave like a cosmic vacuum cleaner. It does not actively consume everything nearby. Most of the time, it is relatively calm. Stars orbit at vast distances, following predictable paths. Gas drifts slowly. The galaxy remains stable. The danger is not explosive. It is latent. That calm hides extraordinary power. The gravitational pull of this black hole helps anchor the entire galaxy. It contributes to the deep gravitational well that keeps IC 1101 bound together. Over billions of years, as galaxies merged, and their central black holes sank toward the center through gravitational interactions, this black hole grew larger and larger. Each merger added not only stars to the galaxy, but mass to its core. Black holes merged with black holes, releasing titanic bursts of gravitational waves and leaving behind a single, even more massive remnant. The scale of that growth defies normal intuition. When two supermassive black holes merge, the energy released is among the most powerful events in the universe. For a brief moment, they can outshine entire galaxies. Not in visible light, but in gravitational radiation ripples in spacetime itself. IC 1101's black hole has likely experienced dozens of such mergers over its lifetime, each one reshaped the core of the galaxy, scattering stars, enlarging the central region, and deepening the gravitational dominance of the final object. The presence of such a massive black hole also explains another paradox of IC 1101, why it is so quiet. When gas falls toward a black hole, it heats up, forming a bright accretion disk and sometimes launching enormous jets of energetic particles. These outflows can heat surrounding gas, preventing it from cooling and collapsing into new stars. In effect, the black hole regulates the galaxy's growth. Too much gas falls inward, and the black hole responds by releasing energy that shuts future star formation down. It is a feedback loop that keeps the galaxy in balance, even as it contributes to long-term stagnation. This is where fear and awe intersect. The black hole is not a destroyer in the dramatic sense. It does not tear the galaxy apart. It shapes it. Its influence is subtle but absolute. Over time, it helps determine which stars form, which gas remains bound, and how energy flows through the entire system. It is a quiet architect of destiny on a scale that dwarfs anything else in the galaxy. The mystery deepens when you consider how such an object forms at all. Even with billions of years and countless mergers, building a black hole of this size pushes the limits of current models. Astronomers can explain the process in broad strokes, but many details remain uncertain. How fast did it grow? Did it begin as a massive seed early in the universe, or did it grow steadily through merger after merger? How many black holes were consumed along the way? These questions remain open, and the answers lie buried in events that unfolded billions of years before Earth even formed. What we do know is that the black hole and the galaxy grew together. Neither is an afterthought. The galaxy's enormous size made the black hole's growth possible, and the black hole's immense power helped shape the galaxy's final form. They are a matched pair, bound by gravity and history. You cannot fully understand one without the other. There is something profoundly humbling about this relationship. At the center of the largest galaxy, we know lies an object that bends space and time to such an extent that our best physical theories are stretched to their limits. It is invisible, unreachable, and yet its presence is undeniable. Everything around it responds. Everything around it knows it is there. This is power at its most abstract. Not force, not motion, not destruction, but inevitability. The black hole does not need to act to be dominant. Its mere existence is enough. And when you step back and see it in context of billions of solar masses embedded in a galaxy millions of light-years wide, itself just one structure in a universe filled with trillions, the sense of scale becomes almost unbearable. Fear arises not because the black hole threatens us, but because it reveals how extreme reality can be without spectacle. All follows close behind, because despite that extremity, the universe remains orderly, consistent, and comprehensible in principle. The supermassive black hole at the heart of IC 1101 is not an aberration. It is the logical endpoint of gravity, given enough time and material. And that may be the most unsettling realization of all. The relationship between a galaxy and the black hole at its center is not a simple one-way story of destruction. It is a system, a loop, a balance that slowly emerges as power accumulates. In IC 1101, this relationship has reached its most extreme expression. The same forces that once allowed the galaxy to grow without restraint now act to suppress further creation, not through intention, but through inevitability. Early in a galaxy's life, growth is relatively straightforward. Cold gas is abundant, gravity pulls it inward, and stars form efficiently. Mergers add mass, deepen gravitational wells, and funnel even more material toward the center. During this phase, the central black hole grows quietly in the background, fed by infalling gas and by the mergers of other black holes brought in by colliding galaxies. Everything points toward expansion. Energy differences drive motion, imbalance fuels change, and creation thrives because there is room for it to happen. But as the black hole grows more massive, its influence begins to extend far beyond its immediate surroundings. Gas falling toward the center no longer settles gently. It heats up, compresses, and releases enormous energy as it spirals inward. That energy does not stay confined. It radiates outward, sometimes as intense light, sometimes as fast-moving particles, sometimes as vast outflows that push against the galaxy itself. Hot gas resists collapse. Without collapse, stars cannot form. What once fed growth becomes an obstacle to it. This is the heart of the feedback loop. Too much inward flow triggers outward force. The system regulates itself. The black hole does not need to consume everything nearby to matter. Its presence alone is enough to reshape conditions across the galaxy. Gas that might have formed stars is heated, stirred, or driven away. Some escapes entirely into intergalactic space. Some remains bound, but unusable. Either way, the long-term result is the same. Star formation slows, then largely shuts down. What makes this process so powerful is that it is self-consistent. There is no external switch that flips when a galaxy becomes too big. The same laws apply at every stage. Gravity pulls inward. Energy pushes outward. When a system becomes massive enough, those forces naturally balance in a way that favors stability over change. Control emerges from chaos. The galaxy and its black hole coevolve, each shaping the other's future without any need for special rules or exotic physics. In IC 1101, this balance has settled deeply. The galaxy is so massive that its own success limits its future. The black hole at its center acts as a regulator, allowing the system to exist but not to reinvent itself. The conditions for large-scale star formation are gone. What remains is endurance rather than creativity. This is not failure. It is the natural endpoint of hierarchical growth. Seen as a whole, the feedback between black hole and galaxy provides a rare sense of closure. It explains why growth does not continue forever. It shows how the same forces that build complexity eventually smooth it away. Power grows until it regulates itself. Complexity peaks, then stabilizes. The silence of a giant galaxy is not mysterious once you understand the system that produced it. It is simply what happens when creation runs out of room and equilibrium takes over. If you let time continue its slow, indifferent march forward, the story of IC 1101 becomes quieter, colder, and far more lonely. Not suddenly, a kitty. But in the way deep time always works through gradual subtraction. Billions of years pass first, trillions follow. And with each step forward, something familiar disappears. In the relatively near future, measured on cosmic scales, the galaxy still looks much as it does now. Its ancient stars continue to shine steadily. Red and yellow suns dominate the light, long past their youthful brilliance, but reliable and enduring. The galaxy drifts through its cluster, gravitationally bound to its surroundings, still part of a crowded environment. From within, nothing feels urgent. Change is so slow it barely registers. But even during this apparent calm, the universe outside the galaxy is changing in ways that cannot be stopped. Space itself is expanding, and not just expanding, but accelerating. Distant galaxies are moving away from one another faster and faster, carried apart by a force we call dark energy. Over time, this expansion stretches the cosmos thin. Objects that are not gravitationally bound drift beyond reach. Light emitted from distant galaxies eventually can no longer overcome the expanding space between them. As billions of years pass, this effect begins to reshape the visible universe from IC 1101's perspective. One by one, distant galaxy clusters fade from view. Their light grows weaker, redder, stretched to longer wavelengths until it disappears entirely beyond a cosmic horizon. The universe, once crowded with structure, begins to empty. Not because galaxies vanish, but because the expanding space between them grows too vast for their light to ever arrive. Within the local cluster, gravity holds on longer. Galaxies continue to orbit, interact, and slowly merge. Over immense spans of time, IC 1101 may absorb what remains nearby, growing slightly larger even as the rest of the universe slips away. Eventually, the cluster itself may collapse inward, forming an even more massive, isolated structure. Beyond it, nothing remains visible. The galaxy becomes an island in an ocean that no longer reflects light. Then the stars begin to change. The most massive stars died long ago, exploding as supernova or collapsing into black holes early in the galaxy's history. What remains are smaller, longer-lived stars. Sun-like stars continue burning for billions of years, but even they are temporary. One by one, they swell into red giants, shed their outer layers, and fade into white dwarfs. The galaxy grows dimmer, not dramatically, but steadily. Trillions of years into the future, the dominant sources of light are red dwarfs, small, faint stars that burn their fuel with extreme efficiency. These stars can shine for tens of trillions of years, outlasting everything else. For a long time, they provide the last gentle illumination in the galaxy. Scattered points of dull red light drifting through the dark. But even they are not eternal. Eventually, they too exhaust their hydrogen and fade. As the final stars go out, the galaxy enters a new phase. No new stars form. No old stars remain shining. What's left is a vast collection of stellar remnants. White dwarfs, neutron stars, black holes, and cold planets drifting in darkness. The structure of the galaxy still exists gravitationally, but visually, it has almost vanished. The once glorious giant becomes a shadow of mass rather than a source of light. This is where cosmic loneliness truly sets in. There are no nearby galaxies visible anymore. No distant points of light beyond the galaxy itself. The universe has become a dark, silent place, punctuated only by the faint glow of residual heat slowly leaking from dead stars. From within, I see 1101. If any observers could exist, the sky would be nearly empty. Not black, because nothing exists, but black, because nothing shines. Time continues to stretch forward, indifferent to memory. White dwarfs cool, radiating away their last heat over spans of time so long that even trillions of years feel brief by comparison. Eventually, they become black dwarfs objects that emit virtually no energy at all. Neutron stars may slowly decay. Black holes persist, longest of all, silently orbiting through the remnants of what was once a galaxy. Even these giants are not permanent. Over incomprehensibly long spans of time, black holes slowly evaporate through a process called Hawking radiation. The most massive black holes take the longest timescales so vast that writing them out strains language itself. But the process is relentless. One particle at a time, energy leaks away. Even the most powerful objects in the universe are not exempt from the slow erosion of time. Eventually, IC 1101 ceases to exist as a recognizable structure. Its matter disperses. Its black holes evaporate. Its remnants drift farther apart as space continues to expand. What was once the largest known galaxy becomes a diffuse cloud of particles spread thinly across an ever-growing volume. No stars, no light, no structure in any meaningful sense. Just matter approaching thermal equilibrium with the cold background of the universe. This future is not violent. There are no final explosions, no dramatic endings. The universe does not end with a scream, but with silence. The loneliness is absolute, not because something went wrong, but because everything played out exactly as the laws of physics allowed. Growth led to dominance. Dominance led to stability. Stability led to stagnation, and stagnation led to quiet dissolution. The emotional weight of this future comes not from fear, but from scale. Everything that once felt immense, galaxies, clusters, even black holes, becomes temporary when viewed against deep time. IC 1101, for all its unimaginable size, occupies only a fleeting chapter in the universe's story. A long chapter by human standards, but a brief one in the full sweep of cosmic history. And yet, there is something hauntingly immersive about imagining this slow descent. Not because it is tragic, but because it is honest. The universe does not promise permanence. It allows complexity to arise, flourish briefly, and fade. IC 1101 is one of the grandest examples of that process. We know a structure so large it defies imagination, and yet still bound to the same fate as everything else. In that far future, there are no witnesses, no memory, no record of what once existed. The galaxy does not mourn its lost stars. Space does not reflect on what has faded. But here, now, thinking across these impossible spans of time, the loneliness feels real. Not because the universe is empty today, but because it will not always be full. And that knowledge lingers. In the far reaches of time, after isolation has become complete and light has thinned to almost nothing, the universe enters a phase defined not by drama, but by inevitability. Within what was once the largest galaxy we knew, structure does not collapse all at once. It erodes, slowly, patiently, with a calm that feels almost deliberate, even though no intention exists. The first to go are the stars themselves. Long before this era, the massive stars vanished in brief, brilliant endings. What remains are smaller, longer-lived suns that burn quietly for trillions of years. Eventually, even these reach the limits of fusion. They swell, shed their outer layers, and leave behind dense cores white dwarfs slowly cooling in the dark. No explosions mark this transition. No sudden violence. Just a steady dimming, star by star, until the galaxy's once abundant light becomes sparse and faint. As time stretches further, even white dwarfs surrender their warmth. They radiate away the last traces of heat over spans of time so long that familiar units lose relevance. Trillions upon trillions of years pass as these remnants cool toward the temperature of empty space. In theory, they become black dwarf objects that no longer glow at all. At that point, stellar death is complete. Fusion, the process that once powered galaxies, has ended everywhere. What remains are the densest leftovers, neutron stars and black holes. Neutron stars, born from the collapse of massive suns, are incredibly stable, but even they are not eternal. Over vast spans of time, interactions, decay processes, and collisions slowly alter their state. They persist longer than stars, but they too are temporary features in a universe moving toward equilibrium. Black holes last the longest. They feel like the ultimate survivors, objects so massive and so compact that nothing escapes them. For an unimaginably long time, they dominate what remains of structure. The supermassive black hole at the center of IC 1101 outlives everything else. A silent anchor in a galaxy that no longer shines. But even black holes are not exempt from entropy. Over extreme spans of time, black holes slowly lose mass through a process known as Hawking radiation. This is not decay in any intuitive sense. It is evaporation so gradual that calling it slow feels inadequate. A supermassive black hole can persist 4 timescales that make the age of the universe seem brief. And yet, particle by particle, energy leaks away. No drama. No collapse. Just the steady subtraction of mass from something once thought permanent. Eventually, even the largest black holes disappear entirely, converting their remaining mass into a faint whisper of radiation that blends into the background of space. When the last black hole evaporates, something profound has ended. There are no longer any dense concentrations of matter capable of shaping their surroundings. Gravity still exists, but it has little left to organize. The scaffolding of the universe has dissolved. With the loss of these anchors, structure itself begins to unravel. Objects drift farther apart as space continues to expand. Any remaining bound systems loosen and disperse. What was once a galaxy becomes a thinning distribution of particles spread across an ever-growing volume. Distinctions fade. Boundaries lose meaning. The concept of a galaxy, or even of location, becomes irrelevant. This is entropy in its purest expression. Energy spreads out. Differences smooth away. Complexity gives way to uniformity. Not because of destruction, but because nothing remains to maintain order. The universe approaches a state where change becomes increasingly difficult, where there are no gradients left to drive motion or transformation. Everything that could happen has already happened. What makes this ending so unsettling is its calm. There is no catastrophe to resist, no moment to fear. The universe does not rush toward its conclusion. It drifts. The erasure of structure feels less like an ending and more like a long exhale. A gradual release of tension built up over billions of years of creation. Acceptance comes from recognizing that this fate is not specific to one galaxy, no matter how large. The largest structures fall to the same laws as the smallest. IC 1101's immense size does not grant it special exemption. It merely means that its story unfolds over longer spans of time. Its end is quieter, not grander. In the deepest future, there is no memory of stars, no trace of galaxies, no record of light. The universe does not grieve this loss, does not reflect. It simply exists in a state of near-perfect stillness. And while that outcome may feel bleak from a human perspective, it is also the most natural conclusion imaginable. Everything that was built has been unbuilt. Everything that was gathered has been spread thin. The universe has done what it always does when left undisturbed for long enough. It has settled. It's easy to let that distant future feel heavy, to see impermanence as loss and quiet as something to fear. But there is another way to understand it, one that shifts the emotional weight entirely. The fact that nothing lasts forever is not a flaw in the universe. It is the reason anything meaningful can exist at all. Impermanence is not what empties the cosmos of value. It is what gives value its shape. Consider where we are right now in cosmic history. Stars are burning. Galaxies are structured. Heavy elements exist. Planets form. Chemistry is rich enough to build oceans, atmospheres, and living systems capable of asking questions about the universe they inhabit. This is not the default state of reality. It is a rare phase, balanced delicately between a universe that was once too hot and chaotic for structure, and a universe that will one day be too cold and diffuse for complexity to survive. We live in a narrow window, and that window will not stay open forever. When you look at the long future, the fading stars, the evaporating black holes, the slow erasure of structure, it becomes clear that the present moment is extraordinary precisely because it is temporary. The universe has not always been this way, and it will not remain this way. There was a time when galaxies did not yet exist, when stars had not ignited, when there was no light to speak of. There will be a time when those things are gone again. We exist in the middle, during the brief era when the universe is luminous, structured, and alive with possibility. Even something as vast as IC 1101 exists only because of this timing. It could not have formed in the early universe when matter was too evenly spread. It cannot persist indefinitely into the far future. When expansion pulls everything apart, its very existence depends on a temporary imbalance, a universe young enough to build structure, but old enough to have allowed that structure to grow enormous. That balance will not last, and that is exactly why it matters. Impermanence reframes significance. If galaxies lasted forever, their existence would be unremarkable. If stars burned endlessly, their light would lose urgency. Meaning emerges because there is an edge, because there is a before and an after. The knowledge that things end sharpens attention. It turns observation into appreciation. The fact that this era will pass makes it worth noticing while it is here. There is also relief in understanding that decline is not failure. The universe is not running out of ideas or falling apart in a tragic sense. It is completing a cycle. Complexity arises, reaches a peak, and gently fades. That pattern is not unique to galaxies or stars. It exists everywhere, at every scale. What changes is the time scale, not the truth of the process. Seeing that pattern reflected in the largest structures we know gives it a kind of dignity. From this perspective, the silence of the far future is not a negation of what came before. It is its consequence. The light that will one day be gone is meaningful precisely because it shines now. The structures that will dissolve are remarkable because they exist at all. The universe does not promise permanence, but it offers something else instead, a chance for complexity to arise briefly and be experienced. And here is where gratitude quietly enters. Not gratitude in a sentimental sense, but in a grounded, perspective-shifting way. The fact that we can even talk about the largest galaxy in the universe means we exist during a time when the universe is transparent enough to be observed and ordered enough to be understood. We are not born into darkness. We are born into a cosmos still bright with structure, still readable, still capable of supporting minds that can trace its history. This reframing dissolves some of the dread. The future stillness does not rob the present of meaning. It gives the present its intensity. It reminds us that this era of stars, galaxies, light, and thought was not guaranteed. It is contingent, temporary, rare, and that rarity is not something to mourn. It is something to recognize. Because for a brief span of cosmic time, the universe allows itself to be seen. There is a final turn in this story that has nothing to do with size, distance, or time, yet somehow includes all of them. It begins with a simple observation. The universe is capable of being understood. Not fully, not effortlessly, but at all. Particles follow laws. Forces obey patterns. Structures emerge that can be measured, modeled, and traced backward through history. And within one small corner of this vast system, intelligence arose that could notice these patterns and ask what they mean. That fact alone is extraordinary. For billions of years, galaxies formed, merged, and evolved in total darkness of awareness. Stars burned, black holes grew. Entire cosmic eras passed without observation or interpretation. Then, on one unremarkable planet orbiting an ordinary star, chemistry became complex enough to think. Matter began to look back at itself. The universe crossed a subtle threshold, not of size or energy, but of self-reference. When we talk about IC 1101, we are not just listing facts about a distant object. We are participating in something rare. That galaxy exists whether or not we notice it, but the act of understanding it transforms the relationship. For the first time in its long history, light that left its stars more than 1 billion years ago is being interpreted, contextualized, and woven into a story. The universe is not merely happening, it is being known. This is where scale turns inward. The same laws that allow galaxies to grow millions of light years across also allow neurons to form networks capable of abstraction. The same physics that governs gravity and fusion also governs chemistry, biology, and thought. There is no separation between cosmic and human processes, only a difference in scale. We are not outside the universe observing it from a distance. We are one of its expressions, temporarily arranged into a form that can reflect. That realization subtly elevates identity. Humanity often feels small when confronted with cosmic vastness, as if size alone determines significance. But intelligence reframes that assumption. A single conscious moment contains something no empty galaxy does: awareness. IC 1101 contains around 100 trillion stars, yet it does not know it exists. It does not know its own size, history, or fate. It simply follows gravity. We, by contrast, can hold all of that in thought. We can understand something vastly larger than ourselves. That asymmetry matters. This does not place humanity above the universe in any hierarchical sense. It places us within it in a different way. We are not the point of the cosmos, but we are a way the cosmos becomes visible to itself. Through observation, measurement, and imagination, the universe gains a kind of internal mirror. When we trace the growth of the largest galaxy, we are tracing the consequences of laws that also made our own existence possible. There is a quiet transcendence in that connection, not because it makes us central, but because it makes us relevant. The vastness of IC 1101 does not diminish human meaning. It contextualizes it. Our thoughts occupy almost no physical space, yet they can span millions of light-years conceptually. A mind weighing less than a kilogram can reconstruct the history of a galaxy trillions of times more massive than itself. That is not trivial. It is astonishing. This perspective softens existential fear. The universe does not feel indifferent in the same way once you recognize that it has produced beings capable of curiosity. The laws of physics did not need to allow for consciousness, but they did. They did not need to permit self-awareness, reflection, or wonder, but they do. Intelligence is not guaranteed in a universe. It is a contingent outcome. And that makes its existence meaningful, not accidental. At the emotional peak of this realization, scale becomes less threatening. The immensity of IC 1101 no longer reads as something that dwarfs us into insignificance. Instead, it becomes part of a shared story. We are small in size, but expansive in comprehension. The universe builds enormous structures, and within one of its smaller ones, it builds the ability to understand those structures. That symmetry is subtle, but profound. There is also responsibility implied here. If the universe can observe itself through us, then observation matters. Knowledge matters. Understanding is not just a human hobby. It is a rare cosmic event. When we learn about galaxies, we are not just satisfying curiosity. We are fulfilling one of the few ways complexity expresses itself at this scale. The universe is vast, but awareness within it is fragile and temporary. This reframing replaces isolation with connection. We are not lost in a universe too big to care. We are embedded in a universe that, through us, becomes aware of its own depth. The largest galaxy ever discovered is not just an object at the edge of imagination. It is a reminder that imagination itself is one of the universe's most remarkable creations. In that sense, the story does not end with darkness or silence. It culminates in recognition. The universe has allowed itself, briefly, to be known. Imagine for a moment that you could exist inside this galaxy. Not as a traveler crossing it, not as a beam of light racing through space, but simply as a point of awareness suspended somewhere within its vast interior. There is no edge in sight, no boundary, just an immense gentle glow stretching outward in every direction, stars scattered so thinly that the darkness between them feels almost infinite. Distances here are not something you move across, they are something you accept. If you looked up at the night sky from within IC 1101, you would not see spiral arms or bright, dramatic features. You would see a quiet, uniform haze. The combined light of stars, so numerous and so far apart that no single one demands attention. The galaxy would not feel busy or violent. It would feel ancient, settled, as if everything that could happen already has, and what remains is endurance. From this perspective, the idea of largesse loses its competitive edge. Size here is not about comparison. It is about presence. You are surrounded by something that took billions of years to assemble, something built from the remains of countless other galaxies, something whose scale no longer announces itself loudly because it no longer needs to. The enormity is not overwhelming in the moment. It is quiet, almost comforting in its indifference. And then comes the realization that reshapes everything. You know this place exists, not because you are inside it, but because across more than 1 billion light-years of space and time, its light reached a small planet orbiting an ordinary star. That light passed through expanding space, through emptiness so vast it defies description, and arrived at instruments built by beings who did not exist when the journey began. Against every intuitive expectation, the signal survived, and someone noticed. There is something deeply humbling about that chain of events. A galaxy millions of light-years across does not announce itself. It does not seek to be known. It simply exists, following gravity, aging quietly. And yet, it has been seen, measured, understood, at least in part. Not by another galaxy, not by some grand cosmic observer, but by fragile minds on a speck of matter that occupies no meaningful fraction of its scale. This is where awe settles in, not as shock, but as stillness. The largest galaxy we know is not meaningful because it dwarfs us. It is meaningful because it can be known at all. The fact that the universe allows structures of such scale to exist, and also allows consciousness to arise that can comprehend them, is a coincidence so unlikely it feels almost deliberate, even though it is not. When this video ends, the numbers may blur. The distances may fade. You may not remember the exact diameter or the exact star count, but what tends to remain is the feeling of scale loosening its grip on certainty. The sense that reality is far more capable than our everyday experience suggests. The memory that somewhere out there, far beyond any possible journey, exists a structure so vast that it quietly stretches the limits of imagination. And perhaps the most remarkable part is this. IC 1101 existed long before anyone knew it was there. It will exist long after this moment passes. But there is a brief window in which its existence is not just physical, but known. A fleeting overlap between immense structure and fragile awareness. That overlap is where meaning lives. You do not need to travel there. You do not need to see it with your own eyes. The fact that you can hold its existence in thought is enough. In doing so, you participate in one of the rarest events the universe allows, understanding across scale. And when you return to the familiar world cities, skies, ordinary distances, the knowledge doesn't vanish. It sits quietly in the background. A reminder that reality is deeper, larger, and stranger than it ever needs to be for daily life. That the universe is capable of building things far beyond our intuition. And, just as remarkably, capable of being known by minds small enough to wonder. That quiet contrast is what lingers. Not fear, not insignificance, but awe. Thanks for watching. See you next time.